Hi, everybody. So, I'm Zach, and I'd like to talk a little bit about the Aztec protocol. Aztec stands for Anonymous Zero-Knowledge Transactions with Efficient Communication, and it is our privacy solution for Ethereum, and a method of enabling confidential transactions. Hang on, this is really not very cumbersome. A bit cumbersome. So, just to give a brief overview of what I want to talk about. First of all, what is our privacy protocol, and also a little bit about kind of the problems and challenges that are being faced with when trying to actually bring private transactions to a public blockchain. Some of the roadblocks that exist and how we intend to solve them, as well as our current existing implementation and a roadmap for our full featured release later this year. So it seems like a bit of an oxymoron. You want to enjoy the consensus benefits of a public blockchain, and in doing so, you need every single participant in that blockchain to be able to validate the integrity of the state of that blockchain. However, if you want private transactions, then by definition, the people validating the state of a blockchain aren't allowed to know about it, which kind of is a problem, one would think. But it can be solved using a rather curious and esoteric branch of mathematics called zero-knowledge cryptography, the kind of the practice of being able to prove mathematical statements about encrypted variables without revealing any secrets. But in my opinion, kind of zero-knowledge cryptography, the zero-knowledge proof, has become a bit of a shibboleth in the Ethereum community. It's espoused as being able to solve all of Ethereum's problems. You can have privacy and scaling solutions, and everything will be sunshine and roses, except there's a bit of a gap between the technical vision and reality. Zero-knowledge proving systems are cumbersome. They are expensive to use because the computation required is intense, both for the client-side proof around the verification of smart contract. And the user experience presents some enormous challenges because it's incredibly fiddly to work with. You have to handle new private keys, you have to construct these zero-knowledge proofs, and you have to kind of transact in a fundamentally different way to what we're used to on Ethereum. And the user experience for Ethereum in general is already quite challenging to begin with. And so how do we solve these problems? How do we bring private assets to public blockchain? Because I believe that this is one of these frontiers that has to be conquered for Ethereum to truly show its, and for blockchains in general to show their promise. Because you can't, as a society, as a culture, we kind of, when we engage in financial transactions, we expect privacy by default. And Ethereum and blockchain technology in general is not going to be able to supplant traditional financial services and financial technologies unless it can also confer this privacy to its users. So how on earth do we do that? In my opinion, this is what I've come up with, kind of the building blocks for what one needs for confidential transactions to be a reality on blockchain today. First of all, I think it is extremely important that if you are, one of the strengths of Ethereum is the fact that anybody can build a smart contract that does whatever logic they want it to do. Unlike Bitcoin, unlike most blockchains out there, which very strictly define the semantics of what a transaction is, Ethereum is completely general purpose. And as a result, it's shown an explosion of creativity and growth. And I think that this customizability has to also be extended into the zero-knowledge world, because if I'm building a zero-knowledge, confidential digital asset, I want my transaction semantics to be customizable. Because if I'm building a syndicated loan or a bond or a mortgage, these all have different edge cases, little niches that have to be accommodated for it to be genuinely workable. And so a zero-knowledge system has to accommodate this. In addition, I think this is extremely important and not talked about often enough, is cross-asset interoperability. It is useful if I can send people a zero-knowledge representation of value, but to date, most zero-knowledge proving systems are restricted to one specific asset class. They don't talk to one another. And that means you can't have confidential cross-asset settlement. And if you can't use that technology's settlements layer, then that massively limits its implications and uses. And so a zero-knowledge proving system has to not only confer customizability to digital asset builders, but the digital assets that are created also have to be interoperable with one another. I should be able to build a zero-knowledge DApp, like a clearinghouse or a decentralized confidential exchange that can interface and communicate with these other confidential digital assets easily and efficiently. And the third point is developer-friendly tools. I came into a process problem from the perspective of somebody who had a problem to solve. We were building a syndicated loan platform, and we needed privacy, and it didn't happen. We didn't have it. So I developed the Aztec protocol, but it's not really. It's a bit of a barrier for adoption if you have to be extremely literate in zero-knowledge cryptography to build these kinds of things. I think it's very important that we have very friendly, easy-to-use tools that can be used by developers. You don't have to know anything about zero-knowledge cryptography, just that it works. In the same way that we can send transactions to a blockchain without having to understand the intricate mechanics of an ECDSA signature. And finally, it has to be efficient, both to construct proofs for user experience and also to verify for gas costs because right now blockchains are very throughput limited, and so obviously if a zero-knowledge proof takes a block's worth of gas to validate, then that's always going to be extremely expensive and not very useful. So how do we solve these? Well, the Aztec protocol, I designed it in order explicitly to solve these problems. It is a privacy protocol, but like most proving systems out there, it's not actually a ZK-SNARK. It uses a slightly older piece of technology called a Sigma protocol, which are kind of a bit of the red-headed stepchildren of zero-knowledge proofs these days because they're not very widely used. Well, I mean, relative to ZK-SNARKs, but we believe they can be used to great effect here. And the Aztec protocol contains a bespoke encryption function, unique to our protocol, which enables people to very efficiently encrypt data in such a way that you can have an embedded range proof inside your encryption. And this is extremely important because range proofs are one of the major barriers towards developing efficient zero-knowledge proving systems. If I want to do some kind of confidential transaction or confidential settlement, if I don't want to show the blockchain how much I'm sending or how much I have, the blockchain, the smart contract, still needs to validate the mathematical legitimacy of the transaction. And in order to do that, you have to perform mathematics on encrypted numbers. And one of the big problems with encrypted crypto systems today is that it's very hard to tell the difference between a positive and a negative number, which is a little bit of a problem when you're dealing with financial settlement. And range proofs solve this, but range proofs are expensive, except this one is not. And so the core of the Aztec protocol is this join split transaction. The idea is we represent value very similar to Bitcoin using an UXTO model, but our UXTOs don't display what's inside them. The actual value of our UXTO, we call them notes, is encrypted. And in order to send value around in our encrypted system, you have to perform this join split transaction, where basically you have some input notes and some output notes, you're going to destroy, notes you want to create. The output notes can have different owners, which is how you transfer value. And what you prove is that the sum of the input notes is equal to the sum of the output notes. But you don't broadcast what's actually inside those notes. And in addition to that, these notes can be worth 0, which is a huge part of why we can provide quite high quality privacy and complicate the transaction graph, because users of Aztec are encouraged to use and create as many zero-knowledge notes as they can, because that massively just dilutes any information you can ever get from the system. So what is a note? The on-chain data, the stuff that's displayed, the stuff that's viewable, is the Ethereum address of an owner, because we design the protocol so that you can store the ultimate arbiter of whether a transaction is legitimate or not is an Ethereum private key that signs an ECDSA signature, a public key, and some metadata. And the private data is obviously the value of the note, and a viewing key, which you can use to decrypt the note, and a spending key you can use to spend it. And as long as this balancing relationship is satisfied, the smart contract doesn't need to know what's inside the notes to know that the transaction is legitimate. So this is a slide about the commitment function and the cryptography behind it. But can I get a show of hands for anybody who knows anything about zero-knowledge cryptography? Wow, that's for more than most people that I ask. Well, I'll do a lightning tour of this now. Basically, the commitment function uses something called a Bonin-Boyer signature, and one of the values of a Bonin-Boyer signature is the basic form is secure under a existential forgery attack, but with some terms and conditions. Basically, with a Bonin-Boyer signature, you can add a randomizing factor onto a Bonin-Boyer signature, and it is still a legitimate signature. And so we use this to create effect, because effectively what we do is we have a trusted setup phase, like a ZK-SNARK, where a very privileged private key, which we use the symbol Y here for, creates a database of signatures, where the signatures are signed over every integer that we allow in our range proof. And the idea is you can take one of these signatures from the signature database, which is widely publicized, and you can add a randomizing factor so that when you present this to the blockchain, nobody can look at that database and figure out which signature you picked, but you can still prove that the trusted setup key owner, overseer person, did sign your the whatever thing you have, and therefore, if they signed it, and you can prove and you can demonstrate that some information about the value inside of it, then our smart contracts know with certainty that that integer, whatever integer is hidden inside that signature, is within the tolerated range. I mentioned this trusted setup and this kind of privileged person who has to destroy this toxic waste. Why? I should mention also that we have a multi-party computation protocol, very similar to the Zcash powers of Tau ceremony, where multiple people, hundreds of people can get involved. Actually, we're taking signups now, so email hello@Aztec Protocol if you want to get involved yourself, where any one of these participants, if any one of them acts in good faith and destroys their toxic waste, then the entire protocol is secure and backed by conventional discrete logarithm assumptions. And so, yes, this is how you convert a monopoly into a range proof. I'm happy to answer questions about it after the talk, but I think maybe I'll skip through this bit and that bit. So I want to briefly go a little bit into what is a Sigma protocol, as opposed to a ZK-SNARK or a ZK-STARK or other kinds of proving technologies. Effectively, you prove an algebraic formula that is expressed in the exponent of an elliptic curve. So how, for example, a ZK-SNARK works is you basically write a program, and that program gets transformed into a polynomial, and if you can solve the polynomial equation, that means you have valid inputs to the program. But the kind of that polynomial it's a representation of your program, whereas in our case, the polynomial is like a direct expression of the mathematics that you're trying to validate. It makes our proofs quite simple to construct and prove. It takes like on the order of milliseconds to construct these proofs, so it's entirely in the realm of a hardware wallet's capability to construct, and it's extraordinarily efficient to verify. Our proofs cost at the moment, with current current day measurements, it costs about 800,000 gas, 700,000 to 800,000 gas to validate a confidential transaction on Ethereum, which is pretty efficient. And there are some planned protocol upgrades in the near future that will drop this down to about 200,000 gas, which then becomes extremely useful for a wide range of applications where currently is a little bit too expensive. And the really important thing about this, in my opinion, is the fact that this common reference string, this kind of piece of shared cryptographic information that is required by Sigma protocol, can be shared amongst different kinds of zero-knowledge proofs. And this sounds a bit esoteric, but it's incredibly important because it means that you can build multiple zero-knowledge proofs that all do different things, and you don't need to perform any extra-traditional trusted setups in order for these proofs to be legitimate. To give an example, what we're doing with the Aztec protocol is we're constructing I guess you can say a grammar of zero-knowledge proofs, a family. If you're a digital asset builder and you want customizable transaction semantics, you can use these proofs in a modular fashion and to prove different statements. And we can continue to add more proofs over time, more exotic proofs, esoteric proofs that people need, the community needs, without having to perform any additional trusted setups other than the very first one we do at the very start. And this is really the key for why we think we can build customizable, compatible confidential assets. It's because right now, if I create a ZK, with a lot of zero-knowledge proving technologies that require trusted setups, if you build a zero-knowledge DApp that has some kind of semantics, and it wants to talk to some other zero-knowledge assets with their own semantics, then none of them can trust one another. They can't trust that their zero-knowledge proving systems they're using are legitimate, that they are secure. Whereas with the Aztec protocol, you absolutely can. And so this is a brief schematic of how it all fits together at the moment. So if you have some ERC20 tokens and you would like a confidential Aztec note because you want to perform some kind of a transaction, you want to send somebody some value and you don't want anybody to know how much, then you can use our Aztec commitment function to convert your tokens into notes. Ideally, you make many notes, and ideally, if you already have some Aztec notes, you mix those in as well to obfuscate kind of the outputs of this transaction. And once you construct a joint split transaction, you give one of your you designate the owner of one of the output notes to somebody you want to send value to. And we have a kind of secret sharing protocol, which means that if I can find somebody's like public wallet, the public identity on Ethereum, and I can construct an Aztec note that only they can spend. We also have a stealth address protocol, which means that you can also construct a bespoke, disposable, single-time wallet for that recipient that only they and you can know for sure is linked to their identity. So if you want anonymity as well as confidentiality, that's how we can do it. And that involves some degree of meta-transactions as well to pay for gas costs. So I mentioned before this family of zero-knowledge proofs, this grammar of zero-knowledge proofs, and this is all brought together by something we're calling the Aztec cryptography engine. Effectively, it's a suite of smart contracts that validate our zero-knowledge proof family. And if you're building a confidential digital asset that uses the Aztec protocol, you can listen to the cryptography engine to answer requests and queries about whether zero-knowledge proofs are valid or legitimate. So for example, if I'm building a zero-knowledge confidential decentralized exchange, and I use the Aztec cryptography engine and the bilateral swap proof to determine whether an order is legitimate, I can then send instructions to those confidential digital assets, and they will know implicitly by just querying the cryptography engine whether the instructions they've received are valid or not. And so this really helps because it prevents an enormous amount of redundant computation. Because if you have like one DApp that's providing instructions to multiple assets, only one zero-knowledge proof has to be validated, which massively reduces the gas costs from the order of millions to about 500,000 for a bilateral swap. And so this is all kind of coalesced into what we're calling at the moment ZK-ERC20, our confidential token standard for Ethereum. And this is not some kind of imagined future tech. We already have working proof of concepts on Ethereum. We deployed them in November last year, a form of zero-knowledge DAI, when we had some fun like kind of trading around confidential DAI notes around the office. So if you look on Etherscan today at the contract, you can see that, yes, I put in at some point 50 DAI, and I sent some notes around, but you don't know how much anybody you don't know how much anybody I sent DAI to has, you don't know how much I have, you just know that the sum total of it all is 50 DAI. And obviously the more people that engage in this confidential crypto system, the greater the quality of the privacy. And so, again, with this confidential token standard, you can have customizable transaction semantics, which I think is going to be so incredibly important for widespread adoption of privacy technology. And so, I mentioned before this cryptography engine, the fact that we're trying to build an ecosystem of zero-knowledge dApps that are all compatible with one another, that can all talk to one another without being crippled by incredibly high gas costs or having to construct like a massive set of bespoke zero-knowledge proofs across a lot of different zero-knowledge proving systems. And we've proposed these as EIPs, 173 and 174, for the cryptography engine and the token standard, respectively. And they've been quite well received so far, and we're absolutely planning ahead with our release roadmap and delivering these technology into the hands of developers. And why has my talk gone away? Come on, sorry. Oh dear. Just a minute. Sorry, having some slight technical problems with my poor old laptop. Oh, come on. Sorry. There we go. Yes, and so this is all being put together and coalescing in our Aztec monorepo. If you are a smart contract developer and you want to tinker around with zero-knowledge assets, then head over to our monorepo. My colleague Paul Berg has written a little like kind of article on how to get started with it all and how to start building your own ZK-ERC20 digital assets today. This is where it's all where all our code and APIs are. So if you want to have a look at that. And what's also on the near term is, I mentioned before, like the gas costs of elliptic curve cryptography are pretty intense because the mathematical the calculations you have to perform, this is the sheer volume of them, this is quite a lot, and so therefore the gas costs are quite high. But we are working on that without having to rely on like protocol improvements we don't have a lot of agency over. VS-Strudel is a little, well not so little smart contract that I wrote which performs a lot of this mathematics, this elliptic curve cryptography, at a substantially more efficient cost than currently can be achieved with precompiled smart contracts, which is traditionally how you do it on Ethereum. And eventually, we plan this will hopefully reduce our verification gas costs by about 20% and can be used by pretty much any kind of zero-knowledge proving system that requires elliptic curve crypto. So hopefully, this will be a little bit more useful than just us. And so our roadmap for the 1.0 release is in this quarter, we're going to be releasing our MVP cryptography engine deployed to testnet so that people can tinker around with the full suite of proofs that we have, as well as releasing our complete proof construction API. We currently have 3 proofs live, and we're planning on extending that to 6 by the time we release our MVP. And in Q2, we will be finishing our trusted setup multi-party computation, producing that database of signatures that will be hopefully have the confidence of the community, because we're going to be involved in the community at every level of this, getting our trusted parties involved as well as community members, individuals that want to get involved. And in Q3, we're going to be launching our production-ready mainnet release, and hopefully then forging ahead with producing zero-knowledge wallets and Aztec integrations and the APIs and tooling that people need to actually start integrating with Aztec, as well as formal verification of smart contracts, because obviously this is bespoke custom zero-knowledge cryptography. We've formally proved that the mathematics of it all is legitimate in our papers, but we want to also naturally prove beyond a shadow of a doubt that our smart contract code is a complete representation of the mathematics, and there are no bugs or no errors. There are no unplanned and unwanted little subroutines. And yep, that's just an appendix. So yeah, that's it. That's the Aztec protocol. Thank you very much.
There's a question over there. Hopefully the staff has got a question. Richard Jackson.
Evening. Sorry, I'm not a mathematician, so a lot of that went over my head. But what didn't go over my head is I'm working with secondary debt trading. Mm-hmm. And obviously you've mentioned syndication, and obviously if we're going to put that into a public block, then there's a lot of private knowledge within the chain that the original borrower and the primary lender and syndication lenders, etc., we don't want anybody else to see. But there are certain things that people do have to see, such as the agency and certain people within the chain. Are you able to allow certain people access to parts of the information up the chain in the block? Or is it as secure as you have stated?
So you absolutely can give people some privileged information about what's going on, because the way that information in Aztec is encrypted requires viewing keys. And these are private keys that if you have them, you can see what's going on, but you can't spend things, you can't interfere with what's happening, you can just view it. And so obviously then you can construct these viewing keys through a secret sharing protocol, which enables multiple people to basically have access to these viewing keys. And so you can absolutely share these viewing keys with an auditor, a regulator, trusted parties that need to see what's going on, whilst keeping it hidden from the rest of the world.
And are those viewing keys restricted to each block, or are they open to the whole chain?
So the viewing keys are unique to every single Aztec note that's created. And so you can derive multiple viewing keys from like a single account if you need that kind of level of generality.
Okay, brilliant. Thank you very much. This question.
Thanks very much for that. I have sort of 2 questions. The first is, what do you think of similar but other approaches like Monero or Zcash? And secondly, it occurs to me that, probably not a very profound insight, but you could run a DEX effectively entirely inside an Aztec node, and no one would have any idea that the DEX was happening inside. Is that true, or is that conceptually wrong?
So I'm trying to think. So effectively, an Aztec note is an encryption of an integer, which uses used to represent token balances. So I think it'd be quite difficult to use that to kind of contain the workings of a DEX in a completely private manner. The way that you can build an Aztec DEX is to take a step back. The Aztec protocol provides confidentiality, which means that you can send and receive value without anybody knowing what's going on inside. However, it is the existence of notes is public. So if I own Aztec notes, everybody knows about it. And if I'm sending Aztec notes, everybody knows about it. And Aztec notes are linked to an asset. So if I'm sending around zero-knowledge DAI notes, people know I'm up to something with zero-knowledge DAI, but obviously those notes could have zero value. On top of that, if you need more a greater degree. If you instead, as well as confidentiality, you need anonymity. So you want people to not know anything about who you are. Then you can use a stealth address protocol on top of that. It's actually very similar to the Monero stealth address protocol to basically hide who you are, because the addresses transacting on the blockchain or transacting these Aztec notes are kind of unlinkable to your real identity. And more importantly, anybody who knows my stealth address wallet can send me value without it being linkable. So I guess you can build a DEX using the Aztec protocol. In fact, we do think that's one of the things you can use it for, because we have quite in the works quite a nice partial order filling zero-knowledge proof, which isn't tremendously expensive, but it is a little bit limited because you do know that trades in a certain asset are happening. It's just not what's inside them. With regards to technologies like Monero and Zcash, actually, I started out with this actually just trying to get ZK Snark confidential transaction system working on Ethereum, but I have to say I'm not sure I got this was particularly the right approach. But at the time I was like, there must be a simpler way of doing this, and I wanted to find it. That took a lot longer than just implementing ZK Snarks. But the result of it is this, which I think has some. I think that the technologies are very complementary. With the ZK Snark, you have extremely customizable logic in your confidential transaction system. You can build very advanced programs. For example, like you can build an entire decentralized exchange that processes 40,000 orders in a block. You can build scaling solutions, but that comes at the cost of a lack of customizability, a lack of generality, because of the fact that you need this trusted setup for each circuit, or either A, you need a trusted setup for every single circuit, or the actual validating a ZK Snark proof becomes extraordinarily expensive. So you do this generality. And in regards to Monero use bulletproofs, which are fantastic technology. I love them. They are also, I believe they've been Dan Bono and his team brought them to Ethereum. They are quite expensive, between 3 and 6 million gas per transaction, depending on the approach. And so for what we're trying to use them for, which is not directly as a scaling solution, but effectively, sorry to take a step back, batching transactions is kind of a very big topic in zero-knowledge cryptography, because the idea is if you can validate 1,000 transactions at once, the actual, the cost of validating the transaction as a whole is extremely expensive, but the marginal cost of adding on an extra proof, an extra transaction, is very low. However, if you take that approach, again, you lose generality. You can only validate 1,000 zero-knowledge proofs if they all are proving exactly the same thing. And so what we wanted to focus on is we wanted to construct a zero-knowledge proving system where it's very efficient to validate a single proof, because then you can make that proof a little bit bespoke, and then you can have these customizable transaction semantics. And so that's why we went with our own approach, because with bulletproofs, then you have extremely expensive transactions to verify. Yeah.
I've got a question. How are you funded, and are you at some point selling tokens? Or a basic question.
I normally defer to my CEO and co-founder Tom at the back there. So we are backed by Consensus. They led our seed round, which closed about 4 months ago, as well as Entrepreneur First. And a few other angel investors. And yes, we are currently fundraising. I will point you to my good friend and colleague at the back there for that. Thank you.
I think you've got a question there.
So one of the problems that a blockchain is designed to solve is double spending problem. And looking at the schema that you described, which is a great way of understanding how it all hangs together, what are the challenges of network latency where I convert to an Aztec node, and I convert to an Aztec node, and I convert to an Aztec node before the rest of the protocol has the opportunity to actually decrement the source values?
So because we built on Ethereum, you can piggyback off of the kind of the consensus guarantees of the Ethereum protocol itself. And so in the same way that you can't double spend an ERC20 token by creating an ERC20 token over again before, on your own separate, with your own blocks, you also can't do the same with an Aztec node. And in addition to that, we have kind of two double spending problems to solve. One is the basic double spending problem that's present in every single blockchain, which we didn't solve because we used just Ethereum's solution for that. The other one is double spending within Aztec, that was the harder problem to solve, because basically it goes back to the problem of positive and negative integers. When you're managing arithmetic on an elliptic curve, your arithmetic is, it's modulo a very large prime number. And so -1 is actually like about like, I don't know, trillion, quintillion. So if I have a John split transaction where the input note is worth 0 and the output note, two output notes worth 1 and -1, like technically the mathematics of that is legitimate, but what I've actually done is created more money than exists in the observable universe, which is bad, which is why we use a range proof.
That's it. All right, let's give it up for Zach.